Hello everyone for this series of vibrational dynamics. Today we are going to discuss about free undamped oscillation 2.21. For this oscillation, to understand the meaning of free means it's natural. Means there is no force acting in the system, right? Then undamped means we don't have any damping system included in the spring mass system. Okay, and oscillation is the process of moving in a cycles like forward and backward. All right. So for free undamped oscillation, for instance, we have this system of spring mass system. You can notice we have a spring which has stiffness K and a mass which is moving freely on the surface as we displace this mass, okay, from its equilibrium at x equal to 0. For example, if we pull it in this direction, right, to the right, then there will be a tension inside the or a tensile force in the spring, and that can cause the spring to try to pull the mass back to this direction, right? So this type of oscillation, or this system will oscillate forward and backward, and we can call that as simple harmonic motion. Simple harmonic motion. Or oscillation. Right? So, at a given time, the displacement of this mass will be determined by the stiffness of the spring and the mass of this object. And how we can find the equation or find out the solution, general solution of this system or the displacement at any given time, we will use the solution for ordinary differential equation for the simple harmonic motion. Xt is equal to the amplitude A cosine omega naught t plus phi. So this is the general solution for the system. At a given time, we can know or determine the displacement. If we know the amplitude, all right, so let's say the amplitude, what's A? Let's define A. A is nothing but the amplitude of oscillation or amplitude of displacement. Amplitude of displacement. right? And this one is nothing but the maximum distance the object can reach. All right, then we can know what's omega naught. Omega naught, as you studied in the previous course, it's nothing but natural angular frequency, and its unit is radians per second, right? Time, we know it's that t is the time and phi is the phase angle. Phi is phase angle, which compensate for correct position. At time equal to 0. All right. So this is the general solution. We should always remember the displacement equation for a simple harmonic motion, which have no damping, right? Let's go to another topic, which defining the period of oscillation. So for full cycle, this mass moving forward and backward, it can create one cycle, full cycle. Similar like when you have a circular. Let's draw a circle. All right, assume this is a circle. All right. So if this line, which has, let's call it R, and this is the position, let's call it A, as this one moving at a given frequency, it will start at position 0, then, which is at the equilibrium, then we reach the maximum amplitude, which is around, let's call it A, and as it's going to rotate, it will come back to its original location or equilibrium status at x equal to 0, then back it will compress the spring again at a distance of minus the amplitude, right? So, and it will keep rotating or going forward and backward. So for one cycle from the center forward, then backward, okay, then again to the center. So this is, we can call it the period time, okay, or the period of oscillation. So the period of oscillation, we can calculate it as T naught. T naught means natural oscillation. Okay, the period will be nothing but 2 pi, which is full cycle, over omega naught, which is how fast it's rotating. Okay. So, and the unit of the period, of course, it's the seconds. We should remember this one because normally this is very simple formula and it may not be found in the formula sheet in the exam. Then there is something else, which is the frequency of oscillation. Frequency of oscillation, which is F, okay, small letter F, and that one you just convert the radians per second or omega naught into hertz, which is 1 cycle per second, and this one will be 1 over T naught, and it will be omega naught over 2 pi. Okay, and its unit is either hertz or 1 cycle per second. 1 cycle per second, right? And this is also an important formula by which, if you know it, you easily can solve some questions in the exam. So in this, now we need to find the equation of motion of this system, right? The equation of motion of this system, right? So normally for many questions, to solve them, we have to find the equation of motion of the simple harmonic motion. So how to find the equation of motion? Firstly, we need to apply Newton's second law. Right? And Newton's second law states that the summation of all forces acting on the mass, which is in here only single degree of freedom because we have one mass, so it's single degree of freedom. Put it O in here. Single degree of freedom, one mass, one coordinate. Right? So it should be the summation of forces acting over this mass should be equal to mass multiplied by acceleration. Acceleration is x double dot in here, which has dot notation. Just to remind you, x is nothing but it is the displacement. The rate of change of displacement, it will be x dot, and that will be the velocity, right? And the rate of velocity will be the acceleration, and this is its notation is x double dot, so this will be the acceleration. Right? So now we need to know the acceleration. We apply Newton's second law over the system. So in this system, you should know what force is acting over them, and you equalize it to mass multiplied by acceleration. If we make the free body diagram for the mass, which is shown in this figure, right, we should indicate firstly whether it's forced or free. It's free now, so the the displacement will be x, right? And you stated the positive coordinate of in the right direction, okay? As the mass is going this direction, right? So what force is acting over it? Of course, as the mass make a tensile force in the spring, okay, this spring, then it will cause a tension inside the spring, and the spring will try to pull back the mass to its to locate it to its at x equal to 0. So the force acting in here will be opposing the direction of motion of the mass, and this force will be the spring force. Normally the spring force, and let me write it down here, spring force. And the spring force, normally we can find it by writing Fs equal to K, which is the spring stiffness, multiply how much displacement you are applying. So, and normally it will be negative, right? Sorry. And this one will be negative, right? So let's rewrite this formula, which is Newton's second law, by writing the summation of forces. Only one force acting over that, and that one will be minus k x equal to m double dot x. So the equation of motion can be written as this way, x double dot. If we move this one to the other side, it will be plus k x, and that one become equal to 0, right? So if we divided both sides of the equation by m, okay, so what you will see, x, this one become m over m will be 1, then we are left with x double dot, then we have k over m multiply x equal to 0. Then this one, right, this equation of motion, the first equation of motion and the only equation of motion of a single degree of freedom. How to solve that problem? How we can find the acceleration of the system? It's very simple. So if we know that, if we know the general solution of the system is this one, right? Displacement. And we would like to determine the acceleration. So xt is equal to amplitude cosine omega naught t plus phi, right? To find x double dot, it's nothing but the second derivative of this equation. So let's try the first derivative. Okay. So x dot, it will be x dx over dt, and that one will become the derivative of this one. So how we can find the derivative of this one? You remember the product rule of the derivative. So it will become, if you have a function f is equal to two functions, the first function, let's call it a, and the second function is going to be p. So the derivative of f will be equal to the derivative of a multiply b plus the derivative of b multiplied by a. So in here we have a, and the a is the amplitude. This is a constant. So the derivative of a constant will be 0. Multiply this one will be 0. The first term will be 0. Then the second term will get the derivative of this one, multiply the constant a. So the solution will be what? A, and derivative of cosine omega t plus phi. The derivative of cosine will be minus sine. So we'll have minus sine omega naught t plus phi, right? And that one should be multiplied by whatever inside in here, because it's the derivative in term of t. So this one will become, this one will be constant, so it will become 0, and we are left, and t, because 2 power 1, then its derivative will be 1. We are left with omega naught. So omega naught will be brought out and become in here. So let's do the next one, which is the acceleration, and that one will become the second derivative of the displacement, or the first derivative of the velocity, and that one will be the derivative of this one. We do the same way. So the derivative of sine will be a cosine. It's not a negative cosine, but a positive cosine. So we'll have minus a omega naught cosine omega naught t plus phi, and derivative whatever inside will be omega naught multiply omega naught will be omega naught squared, right? But remember that we have the term a cosine omega naught t plus phi is nothing but it's the displacement. So this one can be simplified as x double dot minus omega naught squared x, which is the displacement. So we can know that the acceleration can be by understanding by determining the natural angular frequency of the system multiply the displacement, okay, at a given time. So this formula we can bring it in here, and we can rewrite the equation of motion to become we replace x double dot by minus omega naught squared x plus k over m x, and that one become equal to 0. If we would like to know what's omega naught, which is the natural angular frequency, we move it to the other side and we divide both sides by x. So we can cancel x with x. Oops. Let me rewrite it. So it will become minus omega naught x squared x. So k over m x. That one x would be, if you divide it by x, would be 1, and this one will be cancelled. Then omega naught squared will be k over m. Therefore, omega naught, it will become the square root of k over m. And this is the formula which you should always remember, which can help you to find the natural angular frequency of the system. Okay, which system? The system of single degree of freedom. Okay, of the spring mass system. Okay? We have this example, right? This example, a car of a mass 1,500 kilogram, right, is designed to have a natural body bounce frequency of 1.5 hertz, right? So the mass is 1,500 kilogram and the natural frequency F naught is 1.5 hertz, right? What's the effective spring stiffness to meet this requirement? So we need to know what's the stiffness of that, which is K. That's very simple to answer, right? All of you should understand that one and solve it easily. And as we determined in the previous example, we derived the equation for the natural angular frequency as square root of K over M, right? And F naught is omega naught over 2 pi. And omega naught will be, all right, but omega naught then it will be 2 pi f, right? And we know that it's moving 1.5 cycles per second. Okay, so that one becomes 2 pi multiplied by 1.5. If we calculate that, just a moment, 1.5 multiplied 2, you will get 3 pi. Okay, you will get as 3 pi, and that one becomes 3 pi radians per second. Okay, so this is very important that we determine omega naught, and omega naught is nothing but square root K over M. Okay, if we have this one squared, then will become omega naught squared will be equal to K over M. Therefore, K will be omega naught squared multiplied by the mass. So now let's find K, and K will be equal to omega naught squared will be 3 pi. Make sure that you put pi inside the parentheses also. 3 pi squared multiply the mass, which should be in kilogram also, 1,500, and that one become equal to, so 3 squared multiply pi squared multiply 1,500, then the stiffness of that will be what? Should be Newton per meter. So 1, 3, 3, 2, 3, 9.66 Newton per meter. So it become 133.23 kilonewton per meter as a stiffness of the spring. And this is the solution, right? Thank you, and see you for the next session.